you got me all excited about this Far-UVC, and so I'm hoping to save the world with making solid state devices. So thanks to you. Anyways, let me go on. So why do we want solid state UVC? I thought I'd just jump right into the questions that you're asking, Michael Kneisel. It's cost. You know, that's I think that's the big one. So there's broad applications that require orders of magnitude reduction in the cost of delivered Far-UVC photons. Okay, so you know the delivered light that gets to where you want it to go. We want to control the wavelength, and I think the solid state devices will let us control wavelength better. We can, instead of being stuck with what nature gives us, we can vary the alloy concentration in these compound semiconductors and change the wavelength that way. There's the possibility for better beam control. Michael Kneisel talked a little bit about that, but it's possible to get a much smaller n-ton-du. It's a technical term, but it just means you can steer the photons, okay? So you can send them to an optical system and focus them where you want them. And if we go to lasers, and it's part of what I want to talk about, you can do even much better than that. And finally, there's very attractive physical qualities, very small footprint, they're very rugged. You know, so this is what we've talked about with gas lamps in general, being able to replace them. So I guess I want to make that point that it's really cost. So I think that's the big issue. It's going to be cost of delivered photons over time. So, you know, we want to bring that down. So the next thing I want to do is just jump to this thing that Michael showed at the end. And I've heard this quoted a lot about, oh, you know, this shows that you can't get down to short wavelengths. And I really want to make the point that all of us in the community have appreciated that Professor Kneisel has tracked progress over the years, and that's what that was designed to do. So this was primarily the physicists and academics. You can tell in part because we're talking about external quantum efficiency in this, and external quantum efficiency is, you know, physicists love it because that's the fraction of electrons that are converted into photons, right? Very simple idea. It's almost wall plug efficiency. It's just that a lot of the academics think that, well, we'll fix the voltage later. You know, that contacting problem is just an engineering issue. Not quite true, but it's related, right? So this is related to wall plug efficiency, the stuff you care about. And part of my point is that we cared a lot about this UVC for water disinfection. That was driving us. And we didn't care so much about the shorter wavelengths. It was driven in part, I started some work in it back in 2017 or so for doing instrumentation. So that was the primary application we were thinking of that time, not for disinfection. And then after we made some devices, actually, that's when I met David Brenner, Professor Brenner. So I wanted to make the point that because there's interest in it, it's really been moving very rapidly. So this graph was taken from 2018 or 2019, I'm sorry. This is the log plot. So there was a progress by a couple of groups. One of them you just heard from, and another one is Asai Kasei introduced this guy where they're basically taking what they do here and have done it down at shorter wavelength. And then Professor Kneisel talked about this very recent result from his group where they've improved photon extraction and moved it up. But the big point I want to make is that people are putting time into it now, and it's moving. So if you've made this graph as a function of time, you know, 10 years ago, there's nothing down here, right? 10 years ago, there's nothing. So that's the point. This isn't physical. This is just people spending time on making this work. So it's really nitride LEDs are getting better very fast. That's the primary message I want to make you. And the other point I want to make, oh, I'm sorry. Now I have to figure out how to go back. Okay. The other point I want to make is this dollars per milliwatt. So now I'm taking real license, but I think this is an important point that you can roughly estimate the cost because we know what it costs per unit area to make devices up in the blue LED range, right? So that's a well-developed technology. It's a function also of how much production we do. It doesn't do a lot of good to making thousands of devices per wafer if you don't fill the fab. So it's really important, and the semiconductor industry people know this very well, that what drives the increase in wafer size is that you've got a fab facility that you fill, right? So it's an interesting numbers game. You go through it, you get thousands of devices per wafer, and you can do hundreds of wafers at least per week, per month, depending on how you set up that facility. So you can produce tons of these devices, but you've got to have customers that'll use them. Otherwise, they're just, I used to tell people that if you want to buy 10,000 devices, you want to buy one device, it's the same price. And I mean the one price for 10,000, because it doesn't do any good to make one device, right, with semiconductors. Okay. So the point that I'd make is that with these devices, we're already getting less than $10 per device if you would go into production with it, right? So it's not available now, but it's something on production. And the other point I want to make is that these are research devices. And if you look at the history, what generally the devices for sale have lagged by a factor of 10 in terms of efficiency. So when they're actually commercially available, it's a function of how fast it's developing. But you think of how fast it develops, the cycle time of putting something in production, it's been roughly a factor of 10 behind. So that gives you a feeling of what you can expect. There was also a question about semiconductors. I thought I'd put this slide in too, that just gives you a view of wide band gaps and ultra wide band gap semiconductors. So this falls in the category of ultra wide band gap semiconductors. And what I know there's people with very many different backgrounds here, but one of the points I'd make to you is these are what I grew up calling insulators, okay? They're insulators. It's very difficult to dope them. There's only special materials that it's been possible to dope. The AlGaN system is one of them. Boron nitride is another one that's recently come online. And it's interesting, but it's really got a lot of development to do before it starts to compete with the AlGaN system. And it's just tough with these other materials to get them up to the band gaps that you need. To get to this Far-UVC, you're talking about a band gap of 5.3 eV. That's big, okay? So it's something that's difficult to make it work. I was just going to show this picture. Michael showed it as well, but it's possible to make any wavelength up to 210 nanometer just by varying the aluminum and gallium concentration. I say just by varying, but doping is the difficulty with that, or at least it was. So, if ultra-wide bandgap semiconductors have so much potential, what's the problem? A big one has been lack of substrates. These ultra-wide bandgap materials generally require very high temperatures or high pressures. It's difficult to make bulk crystals, and that's something that's been different from other semiconductor technologies. And the other thing is, big one, how do you control the conductivity in these materials? So that's been a key issue in working on these semiconductors, and part of the point I want to make is that's changed recently. So I won't try to explain why that is. Either why ultra-wide band gaps are difficult to dope, or you don't, and it would take me a couple of hours to explain if we're going to go through semiconductor physics. But it's basic fundamental physics that as you make the band gap wider, it's going to get more difficult to dope. So what's new? And I think that's important. Why do we expect progress to be made more rapidly now? One of them is these large substrates available. Michael showed a picture of a 1-inch substrate. I didn't have a scale on there, but you could see those marks through this is a 2-inch wafer. This has been commercially available from one company for a while, and now there's more companies that are coming out with that. So Crystal IS and Hexatech have both had 2-inch now for some time. The other companies coming online, IKZ has started selling 1-inch substrates, and there's a lot of effort in China. So I think this is going to become much more prevalent as we go forward. And actually, Crystal IS has announced that they'll come out with a 4-inch substrate next year. So they showed 3-inch substrates over in Germany, and they're planning to have 4-inch substrates available next year. And the other thing that's new, and this is important too, is that we can do a different type of polarization or a different type of doping than was available before. So now instead of just putting in impurities, it's possible to control the p-type, the whole or positive carriers and the negative carriers, the electrons, simply by varying the alloy concentration. So it's called polarization doping. It's been known for a long time, but being able to get very high quality material, getting very low defect density, has made that possible. So that's new. And one of the things I wanted to show here is that it's possible even to make UVC lasers now. That's something that people have desired to do for a long time, and we've recently demonstrated that with these new materials and with this new type of doping. Bulk substrates are better. The semiconductor industry has worked on this many years with many materials. It's always been better. It's just been with nitride semiconductors, it's been really tough to find a bulk substrate. It's really impressive, the work that's been done on non-native substrates, the type of buffer layers have been grown, but you should understand that's also a cost. At the very least, it's a cost that you have to put in these thicker layers. You have to put in other layers to try to control the dislocations going through it. So there's a lot of things that go into that that are more than just the substrate and the material. So I just wanted to show this picture of a normal semiconductor processing facility. You start with bulk crystal, you make substrates, you grow epi on it, and then you fab it, and finally you singulate it and package it into these little things over here. Where again, there's no scale on there, but you should understand these are a couple millimeter in size typically. The chips are typically a few millimeters in size or 1 millimeter in size, and packages are a few millimeters in size. And this is looking at the epitaxy when you're growing a bulk substrate. They're basically, you can't see dislocations in this kind of material. And that's important because dislocations, they go through multiple layers, those disrupt those layers. So if you look at one of those more in detail, if you see a dislocation going through it, you know there's problems in your quantum wells around that. And again, I just showed this picture. I'm looking at a surface, but you're getting layer by layer or step-by-step flow of growth across the surface, as opposed to a surface that you typically get when you've got dislocations, where you see these individual dislocations going through, and there's steps going around the steps, around the dislocation. So this, I wanted to show this one example. This is a Far-UVC LED structure that we grew a number of years ago now. And it's no longer the best. It was at the time, but this was back in 2019. And my point again is being able to control the dislocation. But I wanted to show also just the difference in how this is fabbed, you know, that you're etching down to this relatively thin layer because it has high conductivity. And so the amount of epi you need is not so much compared to having to grow a buffer layer on the material. And that's some of the device characteristics. One of the points I wanted to make in this was that LEDs typically have a width. So these particular ones, again, there's been new devices made that perform better, but this has about a 10 nanometer width. And that means that you'll get light that'll be longer than the wavelength you wanted, right? So you have to plan for that, either make the device much shorter or put a filter in. You know, that's the approach that, again, Michael Knizel's group is using. So I want to finish this talk by talking about lasers, partly because I want to show you what's new, and partly because I want to show you something that also can be used for better wavelength control and for being able to direct the photons. So this is something that there's a number of applications for it, but I think looking at the Far-UVC makes it particularly attractive. I'm going to kind of move along faster, but I want to make sure I don't run out of time on this. But part of the point I want to make with this is people had tried to make these lasers for many years. There's a lot of funding that went on because there's a number of applications for UVC, and they weren't able to do it. It was something that the Asai Kasei and the Goya group started this in 2017, and by 2019 we had a laser diode made on it. So it was something that was enabled by having the aluminum nitride substrate with low dislocation densities, and by doing the polarization doping. Those were the two key things that let that happen. And what I want you to believe, because it's true, is that this also applies to making the Far-UVC LEDs, that this same kind of technology will enable that to move much faster now. Just some of the characteristics, we were able to make, initially the laser had to be run pulse because of the temperature effects. Now they're able to run CW. There is a strong temperature dependence on that, and that's also something that's indication of defects that we want to improve. So that's the typical of a material that still has room for improvement, to have that strong temperature dependence. But this is part of what I wanted to run for you is just to let you see what it looks like when a laser diode turns on. So this is the package. It's a few millimeters in diameter. As I say, well, I was the psych-assay designated professor at the time, so that's why the psych-assay is on there. So this is below threshold, so you're watching it run as an LED. And then when it hits the threshold current of 130 milliamps, you'll watch it all of a sudden brighten up in the middle, and you've got a beam shooting through it, right? So that's just that last part, all of a sudden, the very directed beam. We're able to make 100 milliwatt diodes at this point. Those are still pulsed. So we still have room for improvement of that, but the photon extraction efficiency is extremely high once it starts to get lazy. So it solves one of the problems we've had with how do we get photons out. In the LEDs, we get lots of photons. Biggest problem is trying to get them out. And I just want to remind people that you know how to direct LEDs. You're used to laser light shows, right? So anyways, we can maybe do that tonight. So So anyway, to summarize, these are the key points. High quality aluminum nitride substrate manufacturing is feasible and cost effective. 2-inch substrates are already being used in manufacturing, and 100 millimeter, 4-inch diameter is going to be available soon. Pseudomorphic growth is special about these materials. It's possible to continue to lattice match to the substrate even as you add gallium to it, and lets you get very high quality material. And that's good for making good devices. Polarization doping is new and lets us be able to get P-type and N-type material, which is crucial for making LEDs and laser diodes. Far-UVC LEDs have been demonstrated, and now we've also demonstrated this UVC laser diode. I just have to show this last slide. I wanted to say this. I thought this was clever, but Far-UVC has a solid future. Okay, solid state future. But I also want to acknowledge the team at Nagoya. So, yeah.
I think given the time, I'll forego any questions, and you can see Mr. Schowalter later if necessary.
Right.
Thank you.